Hello everyone, I'm going to present a series of short lectures on the MRI physics by using a simplified approach. So let's start. So in this first short lecture we're going to talk about magnetism. Let's understand what is the law of electromagnetic induction. So this law says that if you have a moving unbalanced charge, which is essentially proton in the MRI example, so whenever it's moving and unbalanced, it's going to create a magnetic field around it. This arrow denotes the direction of the magnetic moment. So we can use this law of magnetism for the biological tissues because they have water, and the water has hydrogen in it, and hydrogen has protons. And these small protons, they actually act like a bar magnet. They spin on its own axis, and by that spinning, they basically create some magnetic field around it. Atoms with even atomic number cannot be used in MRI, so it has to be unpaired, because the paired protons and neutrons, they're going to cancel each other magnetism. And it turns out that the proton or the hydrogen is the most abundant element in the human body, and it's perfect for the MRI because it has a single proton nucleus. The question is why tissue magnetization does not happen with the Earth's magnetic field, and the answer is because the Earth's magnetic field is very small. It's 0.5 Gauss or 50 micro Tesla, and 1 Tesla is equal to 10,000 Gauss. There are different types of substances with different magnetic susceptibility. For example, ferromagnetic substance, these are the substance that going to experience a force of attraction in the presence of magnetic field. So they have positive magnetic susceptibility, such as iron, nickel, or cobalt. Most biological tissues, they are diamagnetic substances. That means they're going to repel the external magnetic field, and they have negative magnetic susceptibility. And there's a third type known as paramagnetic substances. They are very weakly positive, so less than the ferromagnetic but more than the diamagnetic substances. Okay, so let's see what happens. So when you put a patient in the MRI magnet without anything else, so as you recall, these protons, they are moving, but they are moving in a random direction. So essentially, there is no net magnetic vector. It's also known as NMV. So what happens to the proton magnetism in the presence of an external magnetic field? They're going to align with the direction of the external magnetic field. And the second thing is going to happen is the known as precession, which is the secondary spin around the direction of the magnetic field. We'll talk about that. So let's see what happens. So you put the patient in the external bore, and you see they have aligned themselves. Some have aligned to the direction of magnetic field, and some are opposite. And it turns out that more protons, they're going to line up in parallel rather than the anti-parallel direction, is because this is the lower energy state. So the net magnetic vector is going to be in the direction of B0, and this is what is known as a longitudinal magnetization. So when the protons are placed in the bore of the magnet, they're going to have longitudinal magnetization. Okay, so let's first understand. The longitudinal magnetization is in the z-axis, okay, which is along the axis of the B0. Then you have a transverse magnetization, which is in the xy axis. And then we have a net magnetic vector. We'll talk about that later. So what exactly is precession? That's the second thing that's going to happen to the protons. So this proton is spinning on its own axis. But when we're going to put this proton in an external magnetic field, it's going to have a secondary spin. So still spinning in its own axis, but you can see there is also a secondary spin in the direction of the magnetic field. If you imagine like a spinning top, when it starts to wobble, it's still spinning on its own axis, but it is wobbling down. So there's a secondary spin. That is known as precession. If there is no precession, the most of the magnetization is going to be in the longitudinal direction, in the z-axis. But if there's a precession, there is a potential to develop the transverse magnetization, because there's a shift in the net magnetization vector from the z-axis to the x and y axis. You want to remember Larmor equation, which says that the precessional frequency, or omega, is equal to this gyromagnetic ratio multiplied by the strength of the magnetic field. And you want to remember this value of gyromagnetic ratios for the proton. It's 42.6 megahertz per Tesla. Let's also learn the important concept of phase. What exactly is phase? Now, phase is the position of those magnetic moments in the circular precession path. For example, these three protons, they are moving in their own axis, but they are also precessing, but they are precessing together. That means if you stop at one point of time, you're going to see that these three protons, they are exactly the same point. However, if something happens, especially when you introduce magnetic field, some of the spins, they're going to go out of phase. That means they are not precessing together. So that is known as out of phase. It's a very important concept, so try to remember this. So in the presence of external magnetic field, we know that they start to precess, right? But they are precessing in like a random direction. Okay, so in the nutshell, they are completely out of phase towards each other. So there is no net transverse magnetism. Remember, we talked about when there is a precession, there is a potential to develop transverse magnetism, because the NMV, or the net magnetic vector, shifts from the z-axis to the xy axis. However, because this precession is out of phase with respect to each other of all these protons, so there is no transverse magnetism. That is very important to understand. So what is the recap? We can recap the effect of B0. That means when you put patient in the external magnetic field in the bore, there's an alignment of the protons in parallel and anti-parallel orientation with respect to B0. And it turns out most of the protons, they're going to line up in the parallel direction. So that means your magnetism, or NMV, in the z direction is going to be all longitudinal magnetism. The MXY is the perpendicular component of magnetism, and it's going to be 0 because of all these protons, they are out of phase. So they are at random position. All right, that's all for this short lecture. Thank you.